Hello everyone, so we are on to our next lesson, which is about endogenic processes. And the big idea is that endogenic processes are internal processes that occur within Earth, and these result in the reshaping of the Earth's landforms. So here are the learning competencies that hopefully at the end of this chapter, you guys will be able to achieve. Now, some of the processes that contribute to the changes in Earth's landscape are internal in nature. These processes are called endogenic processes. The energy that drives the endogenic processes comes from within Earth, primarily due to the radioactive decay. I have discussed this before. Radioactive decay involves the disintegration of natural radioactive elements such as uranium-238, thorium-232, and potassium-40 inside Earth. When these radioactive elements decay, they give off heat. The heat is transferred upward, warming the mantle via the mechanism of convection. There are important endogenic processes that played a role in the formation of different landforms. These tectonic processes, like folding, faulting, shearing, and volcanism. So first of all, we have tectonics. Now, as science and technology became more advanced, humans have finally begun to uncover the mysteries of how the inner layers of Earth work, including the processes that are happening in them. So tectonics is the study of the processes that deform Earth's crust, and it is based on the Greek word tecton, which means builder. These processes are manifested on the Earth's surface as earthquakes, volcanic eruptions, and the formation of mountains. Now, early in the 20th century, most geologists believed that the geographic positions of the ocean basins and continents were fixed. However, further studies proved that continents move. A revolutionary explanation called continental drift was proposed in 1912 by Alfred Wegener. So Wegener suggested that all the continents were originally part of a huge landmass or a supercontinent called Pangaea, which was surrounded by a single ocean or superocean called Panthalassa. And according to Alfred Wegener, this is how the Earth looked like around 200 million years ago. Now, approximately 200 million years ago or 240 million years ago, Pangaea began to break apart into smaller continents called Laurasia and Gondwana land. As these two smaller continents fragmented into the continents known today, Panthalassa eventually shrank. Okay, so Wegener hypothesized that all continents were moving apart. Okay, so he noticed how the west coast of Africa, as shown in the picture, and the east coast of South America fit together almost like pieces of a giant jigsaw puzzle. He thought that all the continents might fit together in the same way. Now, to support this theory, Wegener and his colleagues gathered evidences. So what they did is they examined what was known about the climates during the end of the Paleozoic era, around 300 million years ago, and tried to arrange the continents in each geologic period so that the glaciers were near the poles and the hot regions were near the equator. And what they found out is that these are very convincing results that deposits of glacial debris and fossil remains of certain plant species in Argentina, Brazil, South Africa, Antarctica, India, and Australia follow each other in the same succession. Now, another helpful evidence was the identification of Lystrosaurus. Okay, so what they found was actually the skull. So they found it in a sandstone layer in the Alexandria mountain range of Antarctica, and it lived around rivers and swamps around 200 million years ago. Now, why were its bones found in Africa and South America and its teeth in Antarctica? The only explanation was the existence of land bridges or transoceanic bridges which completely disappeared later on, could have connected these continents. So as you can see in the picture, Lystrosaurus is actually the one on the upper right hand corner of the picture. So as you can see, Lystrosaurus, or the fossil remains of Lystrosaurus, can be found in Antarctica, India, and Africa. And if the claim of Wegener is that if continental drift is not true, then how come the fossils are found in different continents? We have to take note that Lystrosaurus is a land reptile. Having said that it's a land reptile, it doesn't have the capability to swim through this vast ocean. So he said that the reason why the fossil remains of Lystrosaurus is found in different continents is because maybe at some point these continents were once together. The same goes with other species that were found, like for example, Cygnanotus, Mesosaurus, and also the plant Glossopteris. Okay, now, another evidence of continental drift came from the study of the magnetic properties of ancient rocks. When iron-bearing minerals harden, their molecules line up and point toward the magnetic pole. Rocks containing iron-bearing minerals have formed throughout geologic time. By studying these rocks, scientists have determined the position of the poles in many different ages, and it was found out that when pole positions are put on a map, the pole appears to wander about. But when the pole positions of the continents of Europe and North America are plotted against time, the results indicate that both continents have adhered similar pole positions. Now, the path of the pole is separated by the ocean. If the continents are put back together, the pole positions would fit. The apparent polar wandering supports the idea of continental drift. Okay, now, despite despite the convincing evidences supporting the existence of Pangaea, the continental drift hypothesis offered no explanation on how and why continents moved to their present locations. So Wegener suggested that continents simply plowed through the ocean floor, and his explanation was actually contradicted by one of the most notable geophysicists of the 20th century. So his name is Harold Jeffreys. So he argued that it is physically impossible for a large mass of solid rock to, just plow through ocean floor without breaking up. Now here comes plate tectonics. So new studies on the ocean floor and earthquakes provided new insights on the behavior of the lithosphere. This led to the development of the plate tectonic theory, and it proposes that the Earth's rigid outer surface, or lithosphere, consists of 7 large and numerous smaller segments called plates. The plates rest upon the viscous fluid like asthenosphere. Okay, the plates move relative to each other. They either move towards each other or move away from each other at a very slow but continuous rate on an average of 5 centimeters per year. Okay, moreover, the movement is driven by the unequal distribution of heat within Earth. The driving force of plate movement is the convection force, in which the warm, buoyant rocks rise and the cooler materials sink. The plate tectonics theory explains the mechanism of the movement of tectonic plates. Like continental drift, it suggested the existence of a supercontinent like Pangaea. It also predicts that the Earth's mass will again form another supercontinent in the future. Okay, now we move on to plate boundaries. So a plate boundary is a fracture separating one plate from another. All major interactions among individual plates occur along their boundaries. There are 3 distinct types of boundaries differentiated by the type of movement. These are convergent boundary, divergent boundary, and transform boundary. First off, we have convergent plate boundary. Now, it is also known as destructive margin. At the convergent plate boundary, what happens is that two plates move toward each other. It is called destructive because crust is destroyed when the two plates converge. The heavier plates dive or subducts beneath the more buoyant plate. Convergent boundaries are called subduction zones. There are three types of convergent plate boundary. We have oceanic, continental convergence. We also have oceanic convergence, and we also have continental convergence. Okay, first of all, oceanic continental convergence forms trenches, destructive earthquakes, and rapid uplift of mountain ranges, as well as building of volcanic arcs, such as the Cascades of the United States and the Andes Mountains of South America. Next, we have oceanic to oceanic convergence, which also forms trenches, such as the Mariana Islands between the Philippine Sea Plate and Mariana Plate, Aleutian Islands between the Pacific Plate and North American Plate, and the islands of Japan. And then finally, we have continental to continental convergence, which forms mountain ranges such as the Himalayan Range and the European Alps. Next, we have divergent plate boundary. Okay, so at the take note, divergent plate boundary is also called constructive margin, and at the divergent boundary, it is also known as spreading center or rift zone, wherein two plates move apart. So as the plates move away, the fractures that are formed are filled with hot magma via upwelling. As the magma continues to rise, it cools to form new crust at the ocean basin. The elevated seafloor forms the oceanic ridge. Okay, the oceanic ridge is characterized by a rugged topography. Along the ridge segment is a deep down-faulted structure, which is called the Rift Valley. So the mechanism of creating new seafloor along the oceanic ridge system is called the seafloor spreading. The rate of spreading is slow. It is spreading on the average similar to that of the plates, which is around 5 centimeters per year. The rate may seem slow based on human timescale, but it is enough to have formed the ocean basins within the last 200 million years. Okay, so a plate boundary can also split apart continental crust. The process is called continental rifting. Rift valleys are formed in continental rift zone. Continental rifting may initiate volcanic activity and magma formation. So next we have transform plate boundary. This is also known as the conservative margin. So a transform plate boundary forms when plates slide horizontally past one another. Conservative margins commonly affect active spreading ridges, producing zigzag plate margin. Most transform faults occur within ocean basins, but there are a few that can be found in continental plates. The San Andreas Fault is one of the few transform faults found on land. So, the Philippine archipelago is formed through the convergence of the Philippine Sea Plate, Eurasian Plate, and the Indo-Australian Plate. So, the Philippine Mobile Belt, or the PMB, is the zone of intense deformation and active seismicity between convergent zones bounding the Philippine archipelago. And it includes two subduction zones. We have the Manila Trench to the west and the Philippine Trench to the east, as well as the Philippine Fault System. The major fault lines in the Philippines include the Marikina Valley Fault, which runs from Montalban to Oriental Mindoro, the Western Philippine Fault, which runs from the Luzon Sea to Sulu Sea. We also have the Eastern Philippine Fault, which is found in the Philippine Sea. We also have the Southern Mindanao Fault, which runs from the Moro Gulf to Celebes Sea. And then finally, we have the Central Philippine Fault, which runs from Ilocos Norte to Davao del Norte. So next we have tectonic forces. Now rocks may undergo deformation, which refers to the change in the original shape and size of a rock. The deformation is caused by tectonic forces, and there are three types of tectonic forces that can deform rock. Okay, so first we have compressional force. So compressional forces generate folding and faulting as a consequence of shortening. These occur along convergent plate boundaries, resulting in mountain ranges. Tensional forces cause stretching and thinning of rocks, resulting in faulting. They are common along extensional plate boundaries like mid-ocean ridges. And then finally, we have shearing forces cause rocks to slide horizontally past one another along transform plate boundaries, resulting to extensive fault system. Next, we have tectonic processes. So tectonic processes that occur on Earth may be categorized as folding or faulting. So folding or folds occur when rocks are pushed towards each other from opposite sides. The rock layers bend into folds. Folds are produced by horizontal compressive stresses such as continental-to-continent collisions or collisions at any convergent plate boundary. They may occur in groups and may be large scale or small scale. Okay, in folding there are two types of fold that is formed. So we have anticline and syncline. So the upward arching fold is called anticline. The downward arching fold is called the syncline. Okay, so a dome is a circular or elliptical anticline in which the limbs dip away in all directions. A basin is a circular or elliptical syncline in which the limbs dip toward the center. And this is how they look like, as shown in the picture. Next, we have faulting. So faulting is the fracturing and displacement of brittle rock strata along fault plane. Faults are fractures in the crust along which displacement has occurred. There are different faults based on the relative movement of the blocks on either side of the fault. So first we have dip-slip. So dip-slip fault occurs when the movement of the two blocks is vertical. Examples of the dip-slip fault are the normal and reverse faults. In a normal fault, the hanging wall moves down relative to the footwall. In a reverse fault, the hanging wall moves up relative to the footwall. And as you can see in the picture, this is how normal fault and reverse fault would look like. Next, we have strike-slip. So in strike-slip fault, it occurs when the dominant displacement is horizontal and parallel. Strike-slip faults may be described based on their direction or motion. A strike-slip fault that moves in a left lateral motion is called sinistral fault, while a fault with right lateral motion is called dextral fault. A special kind of strike-slip fault is called transform fault, associated with the movement in mid-ocean ridges. Others occur on land, such as the San Andreas Fault in California. The Philippine Fault is another example of a transform fault.